Good evening everyone. Welcome to another lecture of engineering mechanics. Well, first of all, I'm sorry that it took 1 week for the next lecture of engineering mechanics. I was on leave the last week due to some personal reasons, but I am back and the engineering mechanics classes will resume. So this is lecture number 11, application of friction part 1. And from this lecture, we are going to see different applications of the concept of friction. We will see the application of friction in belts. We will see the application of friction in wedges, in screw jacks, etc., etc. But before we get into the application part, we need to cover a very important topic, and that is impending tipping. And then we will cover the application part in belts and in rolling. So let's see impending tipping, the concept of impending tipping. Now, in order to understand tipping, I will take the example of this. Let's say this is a box, okay, and it is resting on a horizontal floor and you are applying a force. Now, when this box will move, there can be two cases. Case number 1, this box can move by sliding. So if I am applying a force in order to move this box might move like this. So this is known as sliding. And case number 2, this box can move like this. And this is known as tipping. So impending sliding or impending slipping and impending tipping. What is the difference between these two? First of all, impending means it is about to happen. Okay. Why we are using this word impending? Impending means it is just about to happen. It is not actually happening. It is about to happen. It is on the verge of happening. Okay. Impending slipping means the body is about to slip. And impending tipping means the body is about to tip. Let's understand from the engineering mechanics point of view, what is the difference between these two. So let's say we have a box. Okay. Let me draw it with some other color. Okay. So let's say we have a box which is resting on a horizontal surface. Okay. Now, the weight of this box is W, which is acting at the center of the gravity. Okay. This is the center of the gravity. So the weight of this box is acting here. And let's say we are applying a horizontal force in order to move this block towards right. Let's say we are applying a horizontal force like this. Okay. Now understand this. If I draw the free body diagram of this block, let's say this is the center of gravity. Okay. The weight of the block is acting at the center of gravity. This is the force, the horizontal force P. This is the line passing through the center of gravity. Now comes the interesting part. Okay, understand this part. If I ask you the point at which the normal force will act, what will be that point? Most of you will say that it will be G, the normal force between the horizontal surface and the box will act like this. Most of you will tell me this, right? But you will be surprised to know that this is wrong. The normal force does not pass through point G. The normal force actually shifts. Where it will shift? If you are trying to pull the block towards the right side, it is going to shift towards right, somewhere here. This will be the normal force N. If you are not applying the force on this body in horizontal direction, if you are not trying to move it, let's say this force is not there. If this is not there, then the normal force will pass through G. But what happens is, when you apply a force P, then the normal forces, the forces between the block and this horizontal surface, they are no longer uniformly distributed. Initially, if this P force is not acting, the force between the block and the surface are uniformly distributed, so their resultant passes through the center. But when I apply a force to move this block towards right, what happens is, the forces on this side, on this corner, they are greater than the forces on this corner. And you will understand this practically also. Okay, practically also, assume that you are trying to move a block like this. So you will feel that if you are moving it towards this side, then at this corner the forces will be greater compared to this corner, right? Although the entire surface is touching, but the forces at this corner, as I am moving it like this, the forces at this end will be more compared to forces at this end. And due to this, what happens is that the resultant force shifts from the center towards the right. So this is the normal force, and let's say that the distance between G and the normal force, this distance is x. Okay, let's say the width of this block is B. Let's say the width of this block is B. Okay, so this is B by 2, right? From center to here, it is B by 2. This is B by 2. Now this x will be less than or equal to B by 2, right? This x can be maximum B by 2 or it will be less than B by 2. Okay, if the value of x is less than B by 2, if the value of x is less than B by 2, it will be impending slipping or impending sliding. Okay, but if the value of x becomes equal to B by 2, then what is going to happen? If x is equal to B by 2, it means the normal force is acting here at this edge. So then this block will start tipping. So this is the condition of impending tipping. So what is the condition of impending tipping? This value of x becomes equal to B by 2. Okay, I forgot about one force, the friction force here. This is mu into n, So in case of impending tipping, what happens is the entire normal force will be acting at the edge. So in that case, if I draw the free body diagram, it will look like this. This is the center of gravity G. So the weight is acting at G. This is the horizontal force I am applying, and the normal force is now acting at G, acting at the edge, and this is the friction force. Okay, so this is known as impending tipping. This is the condition of impending tipping. Okay, now what type of questions you might get in case of impending tipping, that we will see now. Okay, so this is the question. A block of mass 100 kg rests on a horizontal surface as shown in figure. So this is a very high block. Find the highest position H. Find the highest position H of the force P which will slide the block without tipping. Look at the question, understand what they are asking. Find the highest position H of the force P which will slide the block without tipping. So what we are going to do in this question, we are going to assume that this block is just on the verge of tipping. Till that point, it is not actually tipping. After that, it will start tipping. So we are going to assume that it is on the verge of tipping. So the entire normal force is on the edge of this block. Assuming that condition, apply the equilibrium equation. Draw the free body diagram and apply the equilibrium equation. So this is the block. This is the weight which is acting at the center of gravity. What is the weight of this block? 100 kg and G is 10. So it will be 1000 Newton. Okay. We are applying a force P at a height H. And now we are assuming that force P is how much? Okay, the value of force P is not given. And now we are assuming that it is on the verge of tipping. The friction force will be mu into N. Mu is 0.3. Let's say this is N1. So this will be 0.3 N1. Okay. Now we need to find the value of H. This distance is H. Okay. This distance will be how much? Half of the width. And the width is how much? The width is 100 mm. So this distance is 50 mm. And let's say this is H mm. Okay. Now, understand this. In order to find the value of this H, I can take moment at this point, right? Let's say this is point G. Let me call this point A. So if I take moment at point A, I will get the value of H. But in order to take moment at A and get the value of H, I need the value of P first. So what I am going to do is, I will apply equilibrium equations. From summation of Fy equal to 0, N1 will be equal to 1000 Newton, right? N1 will be equal to 1000 Newton, and from summation of Fx equal to 0, P will be 0.3 N1 means 0.3 into 1000. So P will be equal to 300 Newton. Now we have got the value of P. So in order to find H, just take moment about A. So summation of M at point A is equal to 0. So what will you get? P into H means 300 into H. This moment will be clockwise, minus 1000 into 50. This moment will be anti-clockwise. Moment of N1 and 0.3 N1 will become 0. So 1000 into 50 equal to 0. So H will be 50,000 by 300. I am getting 166.67 mm. Now what is this? This is the maximum height up to which this is not going to tip. If your H becomes greater than this, it will start tipping. Okay. If your H becomes greater than this value 166.67 mm, it will start tipping over. Okay. But if your H is less than 166.67 mm, then you can actually slide this block without tipping. I hope it is clear. And I hope the concept of tipping is clear, right? If your X is less than B by 2, it is impending sliding, and at X equals to B by 2, it is impending tipping. So let's move on to the next topic, and the next topic is belt friction. Understand this topic, belt friction. See, till now we have seen the concept of friction in case of rigid bodies, but belt is actually a flexible body. So how the concept of friction works here, understand. Here you can see that we have a rod over which there is a rope. A rope is passing over this rod. On one side of this rope, we have a weight W hanging, and on the other side, we are applying a force P. Now understand this concept. If there is no friction between this rope and this rod, then this W will be equal to this P. If there is no friction between the rope and the rod, then W will be equal to P. What does this mean? It means tension on both sides of this rope will be equal. That's what we have done in the previous chapter, right? We were assuming whenever there was a pulley, that pulley is frictionless. So tension on both sides of the pulley, tension on the rope on both sides of the pulley was equal. But if the friction is there between the surface of the rod and this rope, then the tension on both sides will be different. Now, why the tension on both sides is different? Let me draw a part of this rope. Okay, let me draw a small part of this rope. So this rope looks like this. Okay, now understand this. There will be one force here. Let me make a bigger picture for you. Okay. Yes. So this is the rope. Okay. Now understand this. There is one tension here and there is one tension here. Okay. The tension will be perpendicular to this surface. Okay. Now understand. There will be normal force acting from here to here. At the center, that normal force will be maximum. At the corners, that normal force will be minimum. So it will be like this. What is this? This is the normal force acting between the rope and the rod. Okay. If you look at this diagram right now, this diagram is symmetric about the center. Right? This diagram is symmetric about the center. So the tension on this side and on this side will be equal due to symmetry. Right? I hope it is clear now that this diagram is symmetric about the center. These forces are equal on left side and right side of the center. So this force and this force must also be equal. Tension on both sides will be equal. Let's say this is T. So this will also be T. Right? But right now we are not considering the friction force. Right now we are assuming there is no friction between the rope and the rod. If there is friction, what is going to happen? Understand. Let's assume that there is impending sliding towards the right side. Let's assume that there is impending sliding towards the right side. So if I am assuming there is impending sliding towards the right side, then the friction force will act towards the left side. Yes. If I am assuming that there is impending sliding towards the right side, friction force will be acting towards the left side, and that friction force will be like this. Yes. Now look at this. Now do you think that this is balanced? Now do you think that this is balanced? We have now extra forces towards right side. Now we have extra forces towards left side. So in order to balance this tension will be greater than this tension. Yes. The friction forces are acting towards the left side. So now left side we have greater forces compared to right side. So this tension must be greater than this tension. So let's say this is T1 and this is T2. T1 is the maximum tension and T2 is the minimum tension. Okay, T1 is the maximum tension and T2 is the minimum tension. Okay, and there is a relation between this T1 and T2. Let's say this is angle theta. Okay, theta is known as the angle of contact. Okay, so this is the angle at which there is contact between the rope and the rod. Now you might be thinking, sir, here it is 180 degree na, so I am not actually drawing the case of this. Okay, I am just taking a general example. Here in this particular case your theta is 180 degree because the rope is in contact like this. from this point to this point. So the angle between these 2 points is 180 degree. Okay. But in general, we can consider it theta. So what is theta? Theta is the angle of contact. What is T1? T1 is maximum tension, and what is T2? T2 is minimum tension. Okay. Now if you solve the free body diagram applying equilibrium equation, you get the relation between T1 and T2. You might be thinking, sir, how to solve? So what you are going to do is, you are going to consider a very small, very small part of this rope. Why very small part? Because right now the normal force is not equally distributed. Arey yaar, assume na, you are holding a body with your hand like this. Okay. So if you hold the body with your hand like this, if you push it, then you can feel that the normal force you are applying on this body will be maximum at the center of your hand. But at the corners of your hand, that normal force will not be that much. It will be minimum. So that same thing happens here also. The normal force at the center is maximum and normal force at the edges are minimum. But if I consider a very small part of this rope, then I can assume that the normal force is equally distributed. I can assume that the normal force is equally distributed. Okay. So we will consider a very small part. We will draw the free body diagram of this very small part of the rope, and then we will apply equilibrium equations on that part, and from there we get a relation between this T1 and T2. So I will write that equation directly. You have to memorize this. T1 by T2 equals to e to the power mu theta. This is the relation between T1 and T2. Okay. Where the theta is the angle of contact. Now remember, this theta must be in radians. Okay. For example, if theta is 180 degree, then you will not write theta equal to 180. You will write theta equal to pi. 180 degree means pi radians, right? 180 degree means pi radians. 90 degree means pi by 2 radians. Okay. 45 degree means pi by 4 radians. Okay. So 1 degree means pi by 180 radians. So just multiply by pi by 180 and you will convert degree into radians. Okay. So whenever you need to use this equation, you use theta in radians only. So this is the equation that we are going to use whenever there is belt friction, whenever there is a belt and there is friction involved. If the friction is not there, then your mu becomes equal to 0. So it becomes e to the power 0, which is 1. So T1 becomes equal to T2. Okay. T1 becomes equal to T2. Theta value can be more than 180. Yes, it can be more than 180 degree. For example, let's say you have completely wound this rope one time. Then theta will become 360 degree. Means 2 pi radian. If it is wound 2 times, okay, then it will become 2 into 360 degree or 2 into 2 pi radians. So it can be more than even 2 pi radians also. It can be any value. Okay. Chalo. So let's solve a few problems based on belt friction. This is the first problem, which is actually an MSQ question. Wow. Let's see. A 300 Newton block is supported by a rope that is wrapped 1.5 times around a horizontal rod. Look at it. It is wrapped 1.5 time, means one complete time, and second only half time. Okay. So 1.5 times it is wrapped around the horizontal rod. Knowing that the coefficient of static friction between the rope and the rod is 0.15, which one or more of the following statement is or are correct? The minimum force P to keep the block in equilibrium is 73 Newton. Maximum force to keep the block in equilibrium is 1055 Newton. Minimum force to keep the block in equilibrium is 96 Newton. And maximum force to keep the block in equilibrium is 1233 Newton. So we need to find the minimum and maximum value of P for which the block will be in equilibrium. Now first you need to understand the situation here. What is happening over here? This is the weight which we are holding by applying a force P. In order to hold this block, we need to apply a certain amount of force. Okay. If we apply a force less than that value, this block will start falling down. For example, let's say the minimum force which we need to apply to hold the block is 100 Newton. Okay, just example. So if I apply more than 100, no issue. But if I apply less than 100, then this block will fall down. Okay. So 100 Newton is the minimum force which we need to apply here in order to hold the block. If you apply more than that, no issue. But if you apply less than that, then the block will fall. Let's say I am applying 150 Newton. What is going to happen? Block will not fall. Let's say I am applying 200 Newton, 300 Newton, 400 Newton, 500 Newton. Block is not falling down. Let's say I am applying 1000 Newton. What happens is the block will not fall down. It will start going up. So 1000 Newton is the force at which the block will start going up. 100 Newton is the force at which the block will fall down. So between 100 and 1000, the block will be in equilibrium. It will neither go down nor it will go up. If the force is less than 100, it will go down. If the force is more than 1000, it will go up. So we need to find that minimum and maximum force. Understand, if I am assuming the block is just about to go down, then the tension on this side will be maximum and tension on this side will be minimum. So your P will be T2, minimum tension, and the weight of block will be maximum tension. I am assuming block is just about to go down. So this will be your minimum tension, this will be your maximum tension. Okay. Now assuming that you calculate the value of P minimum. So T1 by T2 equal to e to the power mu theta. Now here maximum tension I am assuming is the weight. I am assuming it is falling down. So 300 divided by P minimum equal to e to the power mu theta. Now what is the value of mu? It is 0.15. And what is the value of theta? See, it is wound 1.5 times. Okay. It is wound 1.5 times. So understand, what will be the value of theta? Theta will be 1.5 times of 2 pi. It is wound 1.5 times, na? If it is wound 1 time, then theta will be 2 pi. 1.5 time, then theta will be 1.5 into 2 pi, which is 3 pi. Okay. So theta will be equal to how much? 3 pi. Okay. Now what will be the value of this P minimum? This P minimum will become 300 divided by e to the power 0.15 into 3 pi. So it is 72.97 Newton, almost 73 Newton, right? Almost 73 Newton. So the minimum force to keep the block is in equilibrium is 73 Newton, means this statement A is completely right. Yes? Chalo. So now we need to find the maximum force in order to keep the block in equilibrium. So we will use the same equation, T1 by T2 equal to e to the power mu theta. But this time you will assume that the block is going up and this is going down. So this time this will be your maximum tension and this will be your minimum tension. Okay. So you will get P maximum. So calculate the value of P maximum. (300 into e to the power 0.15 into 3 pi). I am getting 1233.36 Newton, means almost 1233 Newton. So the maximum force in order to keep the block in equilibrium is 1233 Newton. So between 1233 and 73, the block will neither go down nor it will go up. Let's say I am applying 1000 Newton, block will remain in equilibrium. 500 Newton, equilibrium. 200, equilibrium. But if I apply less than 73, means if I apply 50 Newton, block will fall. And if I apply more than 1233, means if I apply, let's say 1500 Newton, block will go up. Okay. So in this single question, we have solved actually two different problems. In GATE, they might give you one of these problems. Let's say they are asking you find the minimum force required to keep the block in equilibrium. So you just need to find P minimum. And let's say they ask you find the force, minimum force required to move the block upwards. Then you have to calculate this. Okay. Chalo. Let's move on to the next question. The next one is really interesting. The seaman pulls with 100 Newton force and wants to stop the motorboat from moving away from the dock. Can you see? This boat is trying to move away from the dock. Okay, let's say the boat belongs to this person. Okay, so now what he is doing is he is stopping the boat. In order to stop the boat, he has this rope. Now what this man does is he is actually expert in engineering mechanics. So he wants to use friction in order to reduce his effort. Okay. So what he is doing is he has wound this rope around this pole. What happens when he wounds this rope around this pole? Friction will come into picture and now he does not have to apply a lot of force here. In order to reduce his effort, he will wound this rope multiple times around this pole because it increases friction. Now they are saying that this man can only apply a force of 100 Newton, whereas the motorboat has a thrust of 3500 Newton. Means the motorboat is pulling this rope with 3500 Newton force, but the man can only generate 100 Newton force. So how you can balance this 100 Newton with 3500 Newton? Sorry, how you can balance 3500 Newton with 100 Newton? You will wound this rope multiple times, n number of times. Okay. In order to find how many times he needs to wound this rope, we need to find the value of theta. Okay, so we will use this equation T1 by T2 equals to e to the power mu theta. What is the value of T1 now? Maximum tension, obviously it is this 3500 Newton, right? What is minimum tension? Obviously it is this 100 Newton, equal to e to the power mu. What is the value of mu? 0.2 into theta. Okay, so this will become 35 equal to e to the power 0.2 theta. Now I am going to take anti-log. How to take anti-log? This is e na, so I will take natural log. If this is 10, then I will take log base 10. So e, so we will take natural log on both sides. So it will become natural log of 35 equal to natural log of e to the power 0.2 theta becomes 0.2 theta. Okay, so I have taken anti-log. So from here I will get the value of theta. Theta will be natural log of 35 divided by 0.2. (17.77). 17.77. Theta is 17.77, but this is in radians. Okay, now we need to find how many times it is wound na? So theta is 17.77. This 17.77 is actually n times of 2 pi. So from here you get the value of n. N will be 17.77 divided by 2 pi. For example, if this was 4 pi, then n would have been 2. So 17.77 divided by 2 pi, it is 2.828. Now understand this. In order to hold this boat, the minimum n can be 2.828. But he cannot wound the rope 2.828 times. He can either wound it 2 times or 3 times. So now what you need to do is you need to take a value greater than this. So you will take n equal to 3. You cannot take less than 2.828. You can take more, but you cannot take less. If there is more friction, no problem, but it should not be less friction, na? So you will go a value slightly greater than this. N will be equal to 3. So your answer will be C, 3. I hope it is clear to you. I hope it is clear to you. Okay. Even if this value was 2.08, let's say this value was 2.08. Will you equate it with 2? Will you round it off to 2? No. Even if it is slightly greater than 2.2 na, even if it is slightly greater than 2, you cannot go less than that value. Even if it was 2.08 na, you will still take 3. You cannot take 2. Although it is very near to 2, don't round it off to 2. Round it off to 3. Because it cannot be less than this value. Whatever value you are getting here na, you can take a value more than that, but not less than that. So even if it was 2.08, I will still round it off to 3, not 2. I hope it is clear. Okay. Chalo. So you will get these type of questions based on belt friction. Very easy questions. Okay. Let's move on to the next concept, which is the concept of rolling resistance. Now understand what is the meaning of rolling resistance. Okay. In order to explain the concept of rolling resistance, what I am going to do is, I will consider a wheel. Okay. Now understand. What do we mean by rolling, beta? What do we mean by rolling? What is rolling? Sleep. If this is a cylindrical body, if I am moving it like this, this is sliding. But if I am moving it like this, then this is rolling. Okay. If it is moving like this, it is sliding. And if it is moving like this, it is rolling. Okay. So let's say we have a wheel which is resting over a horizontal surface. Now the horizontal surface will be something like this. Due to the weight of the wheel, there will be slight deformation on the surface. So the wheel is not actually resting at a point. The wheel is actually resting over a small area. Okay. Now understand this very important concept. Okay. Let's say this is the center of gravity G. The weight of the wheel will be acting here. Now understand this. The normal force between the wheel and this surface will be distributed from this point to this point over a small area. Okay. If you are not applying any force in order to move this wheel, that normal force will be passing, the resultant of normal force will be passing through the center. The normal force from here to here will be equally distributed and the resultant will be passing through the center. Just like I have explained you the concept of tipping. But let's say we are applying a force here. Let's say we are applying a force here in order to move this block. What is this P? P is the force applied to move the wheel at constant velocity. Now understand the meaning of this. P is the force applied to move the block at constant velocity. Here this wheel is moving. Okay, the wheel is moving, but I am assuming that it is moving at constant velocity. I am applying a force P in order to move this wheel. So wheel is actually moving, but it is moving at constant velocity. So right now the wheel is in dynamic equilibrium. I can apply equilibrium equations here. Okay. So right now we are considering the concept of rolling in statics. We will use this same concept of rolling in kinetics also. But here, although the wheel is moving, it is moving at constant velocity. We are assuming that it is moving at constant velocity. Yes, we can apply the force anywhere. Right now I am just assuming that I am applying the force at G. Okay, you can apply it anywhere, beta. So the wheel is moving, but it is moving at constant velocity, means it is in dynamic equilibrium. Okay, now understand this. If I draw the free body diagram, what I am going to get? Now understand this. There will be a normal force between the wheel and the surface. Will the normal force pass through G? Some of you will say yes, but again you are wrong, beta. We have just covered this concept. If I am trying to move this wheel towards right, then this force will shift towards right, na? This force will shift towards right. Now understand this. Very beautiful concept, okay? This is the normal force N. Okay, it has shifted by a particular distance. The distance by which this force is shifted, let me consider it B. Now this B is known as coefficient of rolling resistance. Now you might be wondering, what is this? So beta, in case of rolling, what happens is we don't use the coefficient of friction mu. Here we use another coefficient which is known as coefficient of rolling resistance, which is the distance by which the normal force is shifted from the center. Now this value B is also dependent on the material. Okay, what type of material is this and this? The surface, the material of the surface and the material of this wheel. So this B value is also dependent on the material only, just like mu, okay? But there is a difference between mu and this. Mu is just a number, it has no unit, it is a unitless quantity, but this B is not unitless quantities, it is usually denoted in mm, okay, although it can also be denoted in meter, centimeter, inch, whatever, but it has the same unit as distance, because basically it is distance only, na? So it is usually denoted in mm, okay. Now comes another very important part. In case of rolling, the friction force is not necessarily mu. The friction force is less than mu n. Okay, the friction force is not necessarily mu n, it is less than mu n. For impending rolling, this F is less than mu s into n. Now we will get into the detail of this concept later when we will study kinetics. Right now we will not have to calculate the value of F. Usually in problems you will have to calculate either the value of P or the value of B. Okay, but don't consider the friction force to be mu into n. The friction force will be actually less than mu into n. When we will study the concept of rolling in kinetics, there we will get into the detail of this. We will calculate the value of F and we will actually check whether it is less than mu into n or not. if it becomes greater than mu into n, or if it becomes greater than mu into n, it means there is sliding happening. Okay, so then the concept of rolling is not applicable. So if you are assuming that the wheel is rolling, then the F will be actually less than mu into n. So here we will write the friction force not to be mu n, we will write the friction force just F. Okay, so this is the concept of rolling resistance. Now what type of questions you will get? Let's solve one of these questions. This is the questions that you can get in case of rolling. Okay, now understand this, we will solve lot more problems on rolling in kinetics. Okay, so here this is the case of rolling in statics. So there will be very simple problems of rolling here. Okay, difficult problems of rolling comes in kinetics. There we will get into the detail of this friction force, what will be actually friction force and all that. So understand, read the question. What is the question? The lawn roller has a mass of 80 kg. If the arm BA is held at an angle of 30 degree from the horizontal and coefficient of rolling resistance is 25 mm, determine the force needed to push the roller at constant speed. See, they have written that we need to push the roller at constant speed. So there will be dynamic equilibrium. So then you will know that this is a question of statics. Okay. Neglect friction developed at the axle and assume resultant force P acting on the handle is applied along BA. Chalo. So let's solve this problem. So what we are going to do is, we are going to draw the free body diagram of the roller. Okay. So this is the roller. Center of the roller is A. So we are applying a force P at an angle of 30 degree. Like this. Okay. Now weight of this roller is how much? Let's assume G equal to 10. So weight will be 800 Newton. It will act like this. Okay. Now normal force. So normal force will be shifted. Now this time we are actually moving the roller towards left side. So normal force will be shifted towards the left side. Na? So this will be your normal force, and by how much distance will it shift? Coefficient of rolling resistance is given 25 mm. So this distance is 25 mm. Okay. And the friction force will be acting like this. Don't write it mu into n. This will be F. Okay. Now understand. We need to find the value of the P. Let's consider this point to be point D. I will not write it C because usually C is for center. So if I take moment at point D, I will get the value of P. Moment of F and N both will be 0. You will get moment of 800 Newton and P. Na? Now in order to find the moment of P, I will resolve the P into two components. This is P cos 30 and this is P sin 30. Okay. So let's take moment at point D. If I take moment at point D, moment of F and N becomes 0. You will get moment of P cos 30, P sin 30 and 800 Newton. Okay. Moment of P cos 30 will be anti-clockwise. moment of P sine 30 and 800 will be clockwise. Okay, so it will be P sine 30 multiplied by 25 plus 800 multiplied by 25. So moment of P sine 30 and 800 both are clockwise, both I have considered positive. Now moment of P cos 30. Now understand a very important concept. Okay, what will be the distance between D and P cos 30? So this distance is actually slightly less than the radius, right? This D point is above this point. From this point to center, the distance is equal to radius, but D point is slightly above this, na? So the distance will be slightly less than radius, but here we will ignore that very small distance. We will ignore that very small difference. We will assume that the distance from D to P cos 30 is almost equal to radius. And what is the radius? 250 mm. Okay. So I will consider it to be 250 only, because if you want to calculate the actual distance of D, it will be very difficult for you, and it will be very slightly less than 250. Okay, slightly less than 250. It will be 249.98, something like that. So we will ignore that and we will assume it to be 250 only. Now by solving this equation, we will get the value of P. So tell me, what is the value of P? I am getting 98.03 Newton. Are you also getting the same? 98.03 Newton. 800 into 25 divided by 250 cos 30 minus 25 sin 30. So it is almost 98.03 Newton. So if you apply 98 Newton at 30 degree, this roller will start rolling at constant velocity. Okay. So I hope this question is clear on rolling resistance. Chalo. Now comes the next question. A 100 Newton steel wheel shown in figure has a radius of 100 mm and rests on an inclined plane made of soft wood. If theta is increased so that the wheel begins to roll down and the inclined with constant velocity when theta is 1.2 degree, coefficient of rolling resistance is. So in this question, we need to find the coefficient of rolling resistance. Okay, we have a wheel which is made of steel, okay, and it is resting on a soft wood, and theta at which it is going to roll with constant velocity is 1.2 degree. So what will be coefficient of rolling resistance? Okay, so we will assume that it is rolling at constant velocity, and assuming that, we will draw the free body diagram. Now as it is on inclined plane, I will resolve all the forces normal and parallel to the surface. So weight of 100 Newton I will resolve normal to the surface and parallel to the surface. Now understand this. 100, this will be the cos component, na? So it will be 100 cos 1.2 and 100 sin 1.2. Okay. Normal force will shift. So it is actually rolling towards left, na? So it will shift towards left only. So this is the normal force N. and friction force will be opposite to the motion. So this will be F. Okay. So what is this distance? This distance is B, which is not given actually. Okay. So now we need to find the value of this B. So again we are going to do the same thing. Okay. Let's say this is center of gravity G and this point is A. If I take moment at point A, the moment of N and F will be gone and I will get the moment of 100 sine 1.2 and 100 cos 1.2. Moment of 100 cos 1.2 will be 100 cos 1.2 multiplied by B, and it will be clockwise. Moment of 100 sine 1.2, so 100 sine 1.2 multiplied by, the distance will be slightly less than 100, but I will assume it to be 100. So from here I will get the value of B. Okay. So distance of 100 sine 1.2 from A, it is not actually 100, it is slightly less than 100, but I will assume it to be 100. So 100 sine 1.2 into 100 divided by 100 cos 1.2. So I am getting 2.0947, means 2.095 mm. So this is the answer. This is the coefficient of rolling resistance between the steel and the wood, 2.095 mm. So that's all for today. We will see some more applications of friction in tomorrow's lecture. In tomorrow's lecture, we are going to cover wedge friction and the concept of friction in screw jack. So I will see you guys tomorrow at the same time. Till then, bye bye. Take care. Good night.